Welcome everyone. Today we have Lesson 2 of AP Calc AB, Derivative Rules and Shortcuts. We will introduce all of the derivative rules and shortcuts that you need to memorize so that you do not need to use the limit definition to find derivatives. To begin, let's recall that derivatives help us find an instantaneous rate of change, which amounts to the slope at a single point. This slope would match the slope of the tangent line. Let's look at some points on the given curves. What would a tangent line look like at these points? And, importantly, what are the slopes of these tangent lines? Do they have positive or negative slopes? Where on the curve would the tangent line have a slope of 0? If we look at the curve on the right, we see that a tangent line would have a negative slope at the leftmost point, a positive slope at the rightmost point, and 0 at the middle point at the very bottom of the curve. Based on this discussion, you should be able to see when the curve has a slope that is negative, positive, or 0. But when is a function not differentiable? In other words, when would we say that the derivative, or slope, fails to exist? A function is not differentiable at points that mark discontinuities, corners, or cusps. This means that a function is only differentiable where it is continuous and smooth. There cannot be any jagged edges to the curve. As a result, there is a special relationship between continuity and differentiability. Do you see what it is? A function must be continuous where it is differentiable. However, a function may or may not be differentiable where it is continuous. Let's look at the function with a corner. It is continuous at the corner point, but it is not differentiable here. Make sure you understand this fact about differentiability before moving forward. What is the notation for first, second, and higher order derivatives? If y is a function of x, the first derivative is y prime, and its second derivative is y double prime. The second derivative is merely the derivative of the first derivative. We can also say the y prime is dy over dx. That is, we have differentiated y with respect to the x variable. Looking at our filled-out table, you should be able to correctly identify and represent the notation for first, second, and higher order derivatives. If y equals 3x minus 5, then what are the first and second derivatives of y? We said before that the derivative will give us the slope of a function. Well, what is the slope of the line represented by y? The slope is 3, so that's y prime. And now, what about the second derivative? It's 0, but why? It is the slope of y prime, which is a horizontal line, and the slope of a horizontal line is 0. Its value does not change, making its rate of change 0. What are the basic derivative rules you need to know? The first one is power rule, which works whenever x is raised to a power. To find a derivative with power rule, we bring down the power as a coefficient, then lower the new power on x by 1. We can use this rule to answer all parts of question 12. Part A has a function with 3 terms, and we can find the derivative of each term, 1 by 1. Only the first term, 3x squared, requires power rule because it represents a function with an ever-changing slope. If we use power rule to take its derivative, we would get 6x. The old power comes down, and the new power is 1 less than before. The remaining terms can be viewed as lines with known slopes. From the term 4x, we get 4, and from the constant, we get 0. F prime of x is equal to 6x plus 4. This function will tell us the slope of f at any point. We just need to plug in the x value to get it. If we plug in -1 for x, the derivative comes out to -2. We have just used power rule to answer part A. Do you see how to keep using this rule in parts B and C? You will have to rewrite the terms that contain x in them as x raised to a power. Once you do, you will be able to use power rule to find the derivative function, so that you can evaluate the derivative function at the specified x value. Part B has a derivative function that is equal to 3 over 2 root x, and the value of the derivative function, when x is 9, comes out to 1/2. Again, we have used power rule to successfully find a derivative function. Now try part C. Pause the video, then check your work, making sure you have the correct answer before moving forward. Here is the derivative function, and the value of the derivative function when x is 1/3. We will continue using power rule in our next problem. Question 13 gives us a piecewise function with 2 parts to it. We are asked to find the values of a and b that make this function differentiable. To do this, we will first need to make sure that the function is continuous. This is a prerequisite for differentiability because functions that are differentiable must also be continuous. Then, we need to make sure that the two pieces come together with exactly the same slope. Are you starting to see a route forward? Let's start by ensuring continuity at x equals 1. By setting the two pieces equal to each other and plugging in 1 for x, we get a simplified relationship between a and b. We do not have any answers at this stage, so we can move on, ensuring differentiability at x equals 1. This is where derivatives come into play. We need to set the derivatives of our two pieces equal to each other, specifically when x equals 1. Doing this shows us that b must be equal to 2. Knowing this, we can now find the value of a. A comes out to -5. We have just found the values of a and b that make function f differentiable over its entire domain. Here are some notes about derivatives. You should know that the derivative of any constant or any standalone number is 0. You should also know that coefficients stay as we take derivatives, like in this case, where y equals 3x squared. 3 is a coefficient, and this coefficient is going to stay as we take the derivative of x squared by way of power rule. Y prime simplifies to 6x. Now what about terms, which are separated by addition or subtraction? We take the derivatives of terms separately, or one by one, as you can see in this example, where y prime simplifies to 6x plus 6. These are all basic derivative mechanics that you should be aware of and that you should take with you moving forward. Next, we have chain rule. Chain rule is an advanced derivative concept that I'd like to share with you, sooner rather than later. Chain rule requires us to multiply by the derivatives of any inner functions of x to complete our derivative rule. In our first case, we can view x cubed as having an inner function of x, which has a derivative of 1. So we would multiply by 1 to complete our derivative rule. In our second case, the inside function is 2x plus 1, which has a derivative of 2. We follow the tenets of power rule to take the derivative of the outermost function, but then we need to remember to multiply by the derivative of the inside function as well. The completed derivative rule should be 6 times the quantity of 2x plus 1 squared. This is an important rule for derivatives, and one that you should think about every time you need to take a derivative. Next, you will need to memorize the derivatives of all 6 trigonometric functions, as well as their inverses. Let's start with the 6 trigonometric functions. Pay close attention to which ones are positive and which ones are negative. Write these derivatives down and do your best to commit them to memory. This will be required before moving forward in the lesson. Question 14. Find f prime of x in each case. To do this, we need to use the derivative rules that we just covered. See if you can follow along with the steps provided in this video. You will also need to be familiar with your unit circle values to be able to evaluate the derivatives at the specified value. If you have not done so already, you should also memorize the unit circle because one will not be provided to you during the AP exam. So, how did you do? Did you get the correct answers? If you did, you are ready to move forward to the next problem. Question 15 is more challenging, and both parts require chain rule. When you take each derivative, remember to also multiply by the derivatives of the inside functions as well. These are the expressions inside each trigonometric function. For example, part A shows an inside expression of x squared. We need to complete the derivative rule by multiplying by 2x, which fulfills the chain rule element to this problem. Only then do we have a completed derivative rule that we can use to evaluate the derivative function at the specified value. Now, pause the video and try part B. Here are the answers to part B. Did you get the correct result? Let's try to find y prime in Investigation 5. I would recommend rewriting the expression so that you can more clearly see the outermost operation as the squared operation. The inner function is sine of 3x. These are stacked functions, and there are 3 of them: a squared operation, a sine operation, and then the very inside expression, 3x. We need to use the derivative of each one to complete the overall derivative rule. With so many inner functions, the derivative can be difficult to get to, so we will introduce a strategy for simplifying this type of problem, which can be helpful when there are many inside functions to account for. I would first represent the outermost operation as u squared. This means that u is equal to sine of 3x, y prime is 2u times u prime, and u prime is cosine of 3x times 3. We have all the components of y prime, and we can write a completed derivative equation by plugging in our expressions for u and u prime. This completes investigation 5. Are you ready to move forward? You will also want to know the derivative rules for the inverse trigonometric functions. They are less common than the regular trigonometric functions that we just discussed, but they are also worth knowing. Inverse sine and inverse tangent are very likely to occur on the AP exam. Make sure to memorize these before moving on. We will use these rules in question 16. Pause the video to attempt question 16. Notice that part B will require the use of chain rule. Do your best, then check your answers before moving on. So, how did you do? Do you see how U substitution can help you answer part B? You will also need to memorize derivative rules for exponentials and logarithms. By far, e to the x and ln of x occur more frequently than any other exponential or logarithm in the AP Calc curriculum. Be sure to know these. You will absolutely see them on the AP exam. The derivative of e to the x is also e to the x, and the derivative of ln of x is 1 over x. Jot these derivatives down before moving on to the next section. Question 17. Part A has an exponential with base e, but the power is an entire function of x. This should be considered as the inside function, and we will need the derivative of the inside function to complete the rule for f prime. AU substitution can help with this. It gives us a way to organize and find all components required to complete the derivative rule. When you have the derivative rule completed, you will be able to evaluate f prime at the specified value of x. Are you getting the same answers that you see in this video? If you are, then you are correctly finding the derivative of an exponential function, and you should move on to part B. Part B also involves an inside function, where U substitution can help you organize and structure the derivative rule. The inside function that we will call u is x squared. U prime is 2x, and the final derivative rule for f prime should come out to 2 over x. We are now able to evaluate f prime at the specified value. But do you see another way to complete this problem? What if we use rules of logarithms to bring the power of 2 out in front of the logarithm? F of x becomes 2 times ln of x, and we can find the derivative without needing to use chain rule. Pause the video and try part C. Use rules of logarithms to expand the function into multiple logarithms that are easier to derive. Here's the work for part C. Are we getting the same answers? If so, you should feel comfortable moving forward. Now we will discuss product rule. You will need to use product rule every time you take a derivative where 2 different functions of x are being multiplied by each other. The derivative of f times g is f prime times g plus g prime times f. Some students like the mnemonic fig, GIF, as a way of memorizing product rule. It can also help you with memorizing quotient rule too. With quotient rule, we see subtraction between fig and GIF, and the final derivative has a denominator of g squared. We will use these rules to find derivatives in question 18. Part A. I would recommend outlining the functions f and g, the 2 functions being multiplied to each other. We can say that f is x squared plus x, and that g is sine of 4x. We will need their derivatives to complete product rule. Doing so shows that f prime is 2x plus 1 and g prime is 4 times cosine of 4x. We can now piece together product rule according to the Fig-GIF mnemonic. This gives our final answer for y prime. You can use this outlining method to complete parts B and C. Part B is another problem that involves product rule, while Part C will require quotient rule. Pause the video, then check your answers. Here is the answer to Part B. How did you do? Did we get the same result? And now, here is the answer to Part C. If we have the same answers, then you have correctly used product and quotient rules to complete all of question 18. You should move forward to the next problem. Question 19 gives us the graphs of two functions, f and g, and we will need to use these graphs to find h prime when x equals 4. To start this problem, let's write h prime of x according to quotient rule. Note that g is the numerator and f is the denominator, so h prime of x should look like this. Now, from the graphs, we need to find f, f prime, g, and g prime, all when x is 4. The function values are the y values from the graph, and the derivatives amount to the slopes of f and g. You should see that f has a value of 1 when x is 4. And what is the slope at this point on f? It has a slope of 2, found by using rise over run. Let's look at g next. It has a value of 5 when x is 4. And what is the slope at that point? It is the topmost point on g, and it has a slope of 0. We now have all the values that we need to calculate h prime of 4. After plugging in these values, we can say that h prime of 4 is negative 10. Are you able to get this same result? If so, you should move on to Part B. Part B gives us a chart of values for f, f prime, g, and g prime. Before we can use values in the chart, we need to know what the derivative rule is for h of x. This will require us to not only use product rule, but also chain rule. The function f has a 2x inside, and this is why chain rule is important. After we use product rule, we can plug in an x value of 1, and once we do, we can start to see the values we need to get from the chart. The values we will need are f and f prime when x is 2, as well as g and g prime when x is 1. See if you can pick out these values from the chart. We will outline these values in the top right of our page, right next to the chart of values. Pause the video and try to finish the problem on your own. Did you find out that h prime of 1 is equal to 24? If so, you successfully completed Part B. Can you find the equation of the line tangent to f of x at x equals negative 3? To find the equation of any line, we will need to know just two things, a point and a slope. Now, what's unique between the tangent line and the function at the point of tangency? Well, the function and the line both share the same point at this location, and they also share the same slope. This means that the slope of the line will match the derivative of f at this particular x value. Use the function to complete the xy pair, and use the derivative to find the slope. To then write the equation of the tangent line, you can plug these values into point-slope form. After doing so, you will have created the equation of the tangent line. This is a common problem asked on the AP exam, and it boils down to just finding the point of tangency and the slope at this point. Let's move forward to discuss some advanced differentiation techniques. This starts with implicit differentiation. The word implicit means that something is implied or assumed to be true. When it comes to implicit differentiation, it is implied that y is a differentiable function of x. The consequence here is that any time we derive y, chain rule applies, and we must multiply by y prime. For example, the derivative of sine of y is cosine of y times y prime. This is different from the derivative of sine of x, which is just cosine of x. Armed with this knowledge, we are ready to use implicit differentiation, which will be involved in all parts of question 20. In Part A, we can differentiate every term with respect to x. Once we do this, this is what we will find. X squared would go to 2x, y squared would go to 2y times y prime, and 36 goes to 0. Then, we can solve the equation for y prime, which is the goal of the problem. Y prime should equal negative x over y. And we got there by using the implicit differentiation technique. In Part B, not only will we use implicit differentiation, but we will also use it in conjunction with product rule. However, before we do, we can modify the equation in an effort to make it more easily differentiable. I would recommend squaring both sides, but why? The benefit is that it gets rid of the square root, so we don't get bogged down by radicals and the fraction exponents they lead to. Once we do, we will be able to differentiate the equation with respect to x. Make sure to take your time here so that you correctly navigate product rule, which is required to differentiate the left-hand side of the equation. Be careful with the derivative of e to the 2y. Its derivative is 2y prime times e to the 2y. This is due to chain rule. The differentiated equation should read as follows: e to the 2y plus 2x times y prime times e to the 2y equals 0. Do you see how implicit differentiation is tied to chain rule? And do you see how that leads to the y prime part of the equation? We are now in position where we can solve for y prime through factoring. We set the factor containing y prime equal to 0, then we can isolate y prime. And when we do, we should see that y prime is equal to negative 1 over 2x. We have the derivative of y without needing an equation that specifically defines y as a function of x. And this is the power of implicit differentiation. Next, please pause the video to try to complete Part C on your own. Hopefully you remembered to use product rule on the second term. Additionally, the process of isolating y prime to one side involves factoring out the y prime that initially appears twice in the equation. Were you able to get this same answer on your own? If so, take a stab at Part D, pause the video, and circle back when you are ready to check your work. Part D is a much more challenging problem, but some key parts of this problem include using chain rule, which you should see highlighted in red, and getting the y prime terms all together on one side of the equation, so that y prime can be factored out and then isolated to one side. If you were able to complete this problem on your own, you have mastered implicit differentiation, and you are ready to move on to the next section. Question 21. This equation should look familiar because it was the first equation we derived with implicit differentiation. However, this time, we are asked to find the second derivative of y. We will need the derivative of y prime, and this requires quotient rule. Take your time to outline the functions f and g to get f prime and g prime, so that you can correctly put together the derivative with quotient rule. When you do, you should see that y prime occurs in the rule for the second derivative. And this is a problem, because we want the second derivative to be represented in terms of only x and y, not with y prime. We will have to swap y prime out for negative x over y. Making this substitution gives an equation that only has x and y in it. Then, with a little simplification, we will have a better version of this equation, and a better way to represent our final answer. Do you see how we are able to simplify the equation? And were you able to follow along through this entire problem? If so, you are ready to move on to the next section. Investigation 8. Can we use implicit differentiation to find y prime when y is the cube root of x? While we can use power rule to find the derivative of y, it leads to fractions and radicals. What if we use implicit differentiation instead? What if we cube both sides of the equation to get rid of the root, then differentiate the equation with respect to x? Y prime is 1 over 3y squared, and we can use this equation to find the slope at the given point. We just need to use the y-coordinate of 2 into our derivative equation. And just like that, we find that the slope is 1 over 12 at this point on the curve. While we did not need to use implicit differentiation, it is interesting, and perhaps valuable, knowing that we can. Logarithmic differentiation. This advanced differentiation technique draws on the unique properties of logarithms and builds upon implicit differentiation. Here we use properties of logarithms to expand out clunky functions with lots of multiplication and division, so that we do not need to use product and quotient rule. In question 22, let's take the ln of both sides of the equation. Then, let's expand out the right-hand side as much as possible. Remember that multiplication inside logarithms leads to the addition between them, and the division inside logarithms leads to subtraction. Remember also that the exponents can come out in front of each logarithm, which is especially helpful for radicals. After we have completely expanded the right-hand side, we are in a better position to differentiate the equation. The derivative of ln of y is y prime over y. Make sure to consider chain rule when finding all other derivatives in this equation. Once you have differentiated the equation, we can isolate y prime to one side by multiplying over by y. Now remember, y is defined in terms of x, which is given to us by the original equation. We can make this substitution so that we have a derivative that is completely in terms of x. By finding this derivative, we have successfully applied the logarithmic differentiation technique. After this video, you have learned the most important derivative rules and shortcuts that are a part of the AP Calc curriculum. This is arguably the most challenging part of calculus. We will stick with derivatives in the next video, but we will be focused on their application when it comes to analyzing functions in the xy plane. For now, keep up the good work, and I'll see you in the next video.